I would start with some simple expressions and simple algebraic operations. This is about simplifying by collecting the terms, and if we have in here basically a case of 3x minus 7 minus 5x minus y, we know that we will operate the x with x and y with y. So 3x minus 5x would be minus 2x, and then minus 7y minus y would be minus 8y. So just to be clear that we cannot add common terms to each other. So for example, we cannot add 2x plus 3xy. We cannot do this because x is different from xy. The second example on simplification, it is about first expanding the brackets and then simplifying as much as we can. So 4 times bracket c plus 3d squared minus 3 times bracket 4c minus d squared. If I expand these brackets, would be 4c plus 12d squared. Now I need to time minus 3 into that bracket because I have a minus outside with minus 3. So minus 3 times 4c, that would be minus 12c. Minus 3 times minus d squared, minus times minus is plus, so this would be plus 3d squared. So we need to keep that organization going in algebra. We need to be completely organized when we do algebra. Now I need to again find the common terms. 4c minus 12c would be minus 8c, and plus 12d squared plus 3d squared, that would be plus 15d squared. Okay, starting with this basic, I'm just going to move to another a very important topic, and that is indices and their applications. I'm going to start with the rules of indices. I'm just going to try and write all of them in here. So that is starting from a to power of n times a to power of m. So I'm just going to correct this, so that is times. That would be a to power of n plus m, a to power of n divided by a to power of m, a to power of n minus m, a to power of n, all of it to power of m, equals a to power of nm. Then a to power of 1 equals a to power of 0 equals 1. Now on top of these are the most important ones, but on top of these we have other ones like the effect of minus. We can write a to power of minus n equals 1 over a to power of n. We can also relate the indices to fraction powers to roots. So for example, a to power of n over m would be root m of a to power of n. So we come back to those examples. Then we can relate this to fractions like a over b to power of n equals a to power of n over b to power of n. If we combine basically this one and this one, what we get is that a over b to power of minus n would be b over a to power of n. So we're just reciprocating and we are changing the minus to positive. So with these rules, it is very important that we know quickly we can apply it into different cases. So not just knowing the rules is important, but it's more of applying. So you should not try to memorize this, but to try to apply and learn it into when you do a lot of practices. So I just want to start in here. Before going to applications for simplifications, I just want to say that these rules are not basically they can be proved in some cases very easily. So it is not as everything else in maths. There is a logical reason behind these. So we just use the formulas just to simplify our operations, but this is all of these are provable. So just to give you an example, a to the power of n times a to the power of n. So when we look at power a to the power of n means a has been timed to a n times. So that is timed to a has been timed to itself n times. And then we time that to a to the power of m, which basically means times a again times a, but this time a has been timed to itself m times. So if you look at here, we have a times itself n times, then times a times it to itself m times. So if we look at all overall to this, basically that is a times a times a times a, but how many times? That is n plus m. So that is why the answer is a to the power of n plus m. So that is what you see in a to the power of n times a to the power of m equals a to the power of n plus m. So the rest of these also can be proved in a way, but for now just accept this simple form just to understand some reasoning behind these formulas. So with this one now, I'm going to go through application for simplifications, and I'm just going to start with an example here. So just imagine that we have 12 x squared y cubed z divided by 18 x y z squared. So we want to simplify a case like this. So how we are going to use the indices in here? When we want to do this, the fraction is basically like a divide. So we are going to look at number over number, the parts with x over parts by x, parts with y over part by y, and z over z. So 12 over 18, simplification of that, dividing by 6, each one of them would be 2 over 3. Then we have x squared divided by x. So which rule is in here applies? This is the one, a to the power of n divided by a to the power of m. So our a is x, our n is 2, our m is 1. So that is exactly what that formula means, the application means. So that would be x to the power of 2 minus 1, which is x to the power of 1. So we can just write just x, because a to the power of 1 is a, so that would be just 1x. Y to the power of 3, or y cubed, divided by y. With the same reasoning, that would be y to the power of 3 minus 1, so that would be y to the power of 2. Now z divided by z to the power of 2, or z squared, that would be z to the power of 1 minus 2, which would be z to the power of minus 1. 1 minus 2, which is minus 1. Or we can also write this 2xy squared divided by 3z. We can write, instead of z minus 1, we can write 1 over z. And that comes from this one in here. So z to the power of minus 1 would be equal to 1 over z to power of 1, which is z to power of 1 is z, so really z to power of minus 1 equals 1 over z. So we can simplify that into that form. Now, if you go to the next page, we're looking for application of, again, indices for expansions. And when we look at expansions, we can basically find out some cases in here. Some simple expansions, they could be, for example, 3x squared times 2x plus 1 minus x times 5x squared minus 2. So this is similar to expansion that we did in the beginning of this video, with the difference that instead of numbers in the timing to brackets, we have an algebraic format like 3x squared or x timing to brackets. So when we do that, we are looking at 3x squared times 2x. So this would be 6, 3 times 2 is 6, x to power of 3. Which rule that we are using in here? The rule that we are using is this: a to power of n times a to power of m equals a to power of n plus m. So x squared times x would be x to power of 2 plus 1, because we have a 2 and x is x to power of 1, so 2 plus 1 would be 3. In the same way, times 1 would be plus 3x squared. And this time we are again, this time timing minus x. So minus x times 5x squared would be minus 5x cubed. And then we have minus x times minus 2 would be plus 2x. And that would be equal. To complete this expansion, we need to simplify. We need to simplify the terms that they are same, which is like x squared. Sorry, not that x squared, but the ones that are same in here are x cubed. As you can see, we have 6x cubed and minus 5x cubed. So the answer would be 1x cubed plus 3x squared and plus 2x. So that would be the simplified form of expanding these brackets. So if we go to the next page, the other thing that we need to look at here is factorization. When we look at factorization, in total we have 3 different forms of factorization, and we need to check these forms exactly in this order that I'm going to put in here. The first one, we need to check common terms. 2, we want to check difference of 2 squares. Difference of 2 square, and then we have 3 in here, which would be quadratic form. So we need to check exactly in this order when we want to factorize, and otherwise we could be having problem, basically not basically confused about what we need to do. And I will show this with some examples. So just an example in here, we have 2ab squared minus ab equals. So in here, we are going to look at the steps in here. The first one is a common terms. Between 2ab squared and ab, do we have a common term? Yes, we have, and we have a, which is common in between both of them, and b, 1b is common in, again, both of them. It's divisible. Both of them are divisible to a and divisible to b. So the common term would be ab, and bracket. Now we need to find a term that ab times that term becomes 2ab squared, because that is where the we need to keep it organized. When we put this equal in here, we need to write something that basically if we time, it will give the left hand side. So ab times what becomes 2ab squared? That would be times 2b. ab times 2b would be 2ab squared. And then we have the minus, which is the minus in here. I'm just bringing the same minus. ab times what becomes ab? It is 1. So the answer would be ab times 2b minus 1. And as you can see, factorization is completely opposite of expansion. So in expansion of a term, we go from this side to that side. In factorization, we go from the left to right. Now we come to difference of two square. So that was an example for common terms. When we look at difference of two squares, there is a formula for it, and that means a formula is a squared minus b squared equals a plus b times a minus b. Again, this is not just a formula that we consider as a formula. This is basically expansion of this. If you time this a plus b times a minus b, as you know how we time it, you time the a, if you time this and simplify it, it would be a squared minus ab plus ab minus b squared. But minus ab plus ab simplifies. What is there is a squared minus b squared. So in a way, that formula here is just simplification of an expansion. But if you remember, difference of two squares, because a squared and b squared, and we are having minus, so a squared minus b squared equals a plus b times a minus b. So in a reality, in the real scenarios, how we basically apply this for factorization, a simple example would be factorize x squared minus 9. So when we look at x squared minus 9, if we have a factorization, the things that we need to look at, this is a full squared, and this is also a full square, because that is 3 to the power of 2. So in a way, this is same as writing x squared minus 3 to the power of 2. Our comparing to this one in here, our a is x, our b is 3. So a is x, b is 3. So I need to put the right hand side exactly with the same order. So that would be x plus 3 times x minus 3. And this is factorization because we have converted two terms, subtraction of two terms into two separate terms that they are timing to each other. So x minus 3 all times all of x minus 3. So the point in here is that you should have some good idea generally about some special numbers. So if we look at, for example, another example, so you could have 16a squared minus 49. Again, if you look at this, this is still a difference of two squares, because the first one is 4a, all of it squared, minus 49 is 7 squared. So the answer would be 4a plus 7 times 4a minus 7. So you need to be careful about some of the numbers that they are fully squared, or they are sometimes cubes, and when you see them, you need to be, your mind should trigger to think about why I have been given this number in this question. So the numbers that they are full square or sometimes full cube, and you need to be careful when you see them, are 1, 4, 8, 9, 16, 25, 27, 36, 49, 64, and 81. And we can also add numbers like 32, because 32 is 2 to the power of 5. So when you see some of the numbers like this, or 125 or 100, so these numbers are either fully squared or a cube number. So we can take a root 3 or root 2 of these numbers, and that could still be a number. So when you see these numbers in the questions, you need to think about either difference of two squares, or how you can use and why then the numbers they have, these sort of numbers they have been given. So just to give you an example, if we could, if I change this question to a form of 16a squared minus, if I again clear this section here, minus 47, this is not, you can't factorize this. So there is a reason when you have given a full squared number, which is 49. So you need to be alerted, your mind should be alerted when you see these sort of numbers. Okay, the final form of factorization is the quadratic form. So quadratic form, I'm just going to start with the example again in here. So I'm just going to simplify this in here to clear that, and then the example in here would be x squared minus 5x minus plus 6 equals 0. If you look at this example, factorize this, there is no common term in this one. There isn't no common term between x squared, 5x, and 6. It is not difference of two squared, because x squared is squared, but 5x or 6, they are not squared. They're not a complete square. So the third one, which is the quadratic form, and because this is x squared, that does go into a quadratic form. With these cases, you would, so I put this equal to 0. I can just take that off for now. So with these cases, you're going to put two brackets, and then start with basically putting x and x, because we know that x times x is x squared. That would give us the first term. Okay, starting with x and x. Now we are looking for two numbers in here and here to add 2 minus 5 and time to 6. Okay, add 2 minus 5 and time to 6. So if I look at this in here, I will have minus 2 and minus 3. Minus 2 and minus 3, they add up to become minus 5, and they time together and become plus 6. So that is one form of these quadratic factorization. Now, and the other forms of quadratic factorization could be the times that when we have a case of, for example, a case like 6x squared minus 5x minus 1 equals to 0. With these cases, when we have the difference between this example and previous example is that we have 6x squared rather than x squared. So again, if I take this out, the options that I have, again, I can put two brackets in here, I could have 6x and x, or I could have 3x and 2x. Either of these, they would give me 6x squared in the beginning. Now I need to look at basically numbers that they would they would complete these expansion to give me 6x squared minus 5x minus 1. So I will come to that example later in the next page. Maybe I can just expand this now, and I will put this in the other side. So just to show how this works, 6x squared minus 5x minus 1, we mentioned that it would be either 6x and x, or we could have 3x and 2x, because in either one of them, 3x times 2x is 6x squared, 6x times x is again 6x squared. Now we need to check numbers in here. We need to check numbers that they time, and the time becomes minus 1. So what are those set of numbers that if we time, it will give us minus 1. The only two numbers that we time and it would give minus 1 is 1 and minus 1. If we time it together, it would be minus 1. We could also check minus 1 and 1, because still, if we time them together, it would be minus 1. The reason that we need to check both sides, because if we put minus 1 in here, plus 1 in here, or if we put plus 1 in here, minus 1 in here, it would be different, because 6x and x are different. Again, we are going to check the same thing in here, minus 1, plus 1, plus 1, minus 1. So we are going to check all of these 4 scenarios based on the fact that if we time two numbers, that would be should give us minus 1. Now, slight point in here, we need to now check. I'm going to write one of them and just show how this is basically how we're going to look at it. So if I write plus 1 and minus 1, I know that 6x times x gives me 6x squared. I also know that plus 1 times minus 1 gives me minus 1. But when we look at timing this bracket in this side to that bracket that side, we are also having that minus 1 timing to that 6x, which would be minus 6x. And this plus 1 timing x would be just x. So minus 6x plus x would be minus 5x, which is exactly giving us that answer there, which is the right answer. Now, so this is the right answer. Just to check one case that it is not the right answer, I'm just going to check one more in here, in the second one, just to see that why this is not the right answer. So if I just put, for example, plus 1 and minus 1 in here, again 3x times 2x is 6x squared, and 1 times minus 1 is minus 1, but this minus 1 times 3x and 1 times 2x, so minus 1 times 3x would be minus 3x. 1 times 2x would be plus 2x. If we add them up, it would be minus x. This minus x is not equal to that 5x. So therefore, this minus 1 and plus 1 and minus 1 in here is not the right answer. Okay, having just check it one more time for the top one, I'm just going to just show it one more time. Minus 1 times 6x is minus 6x. 1 times x is x. So minus 6x plus x is minus 5x, which is equal to that. So this is equal, but in here, this is not equal there. So basically, we have our final answer in here would be 6x plus 1 times x minus 1. If I go back to the previous page in here, so the answer would be in here. I'm just going to write that answer. Now, sometimes in high-level questions, as I mentioned, you need to use possibly two of these three forms, and you need to check it in that order. I want to give you one example. For example, this would be, the example is 2x squared minus 18 equals. If you look at this in this form, it is not a difference of 2 square. And it is quadratic, but still it would require us to consider that the middle term is 0 and do a quadratic form. But the simpler way is that when we check it in this order, we see that there is a common term in here. And common term between 2x squared and 18 is 2. So if I say 2 times x squared minus 9. And now you see that x squared minus 9 is a difference of two squares. So I come in here, I can write equals 2 times x minus 9. X minus, because 9 is 3 to the power of 2, so x minus 3 times x plus 3. So we have the final answer for this one is 2 times x minus 3 times x plus 3. So as you see in this one, we combined 1 and 2 to get the final answer. In some occasions, we need to combine 1 and 3. So first of all, we do a common term, and then it would become a quadratic equation, and then we do the quadratic equation. Okay, so the last time in here, application of solving quadratic equations is when we want, factorizing is when we want to solve a quadratic equation. When we say solve an equation, it means that finding x that satisfies that equation. And normally the question could be in a form of solve, for example, x squared minus 9 equals 0. X squared minus 9, we have already factorized it in here. So if we write the factorization, we will have x minus 3 times x plus 3 equals 0. So x minus 3 times x plus 3 equals 0. So when we have two numbers times 0, so timing to each other and becoming 0. So we have, for example, if I write it in this side in here, if I put a times b equals 0. A times b equals 0 will be satisfied if either a or b are 0, because anything times 0 would be 0. So in here, this would be this equation would be satisfied if just x minus 3 equals 0, or if just x minus x plus 3 equals 0. So we could use this logic and say, from here we could say this could be either x minus 3 has to be equal to 0, or x plus 3 has to be equal to 0. And from here, take the minus 3 to the other side, x equals plus 3, and from here x equals minus 3. So x equals plus 3 or minus 3 would satisfy this equation. In the same way, if we had, for example, the question was solve 6x squared minus 5x minus 1 equals 0, again we factorize it like this and equate each one of these terms to 0. So the answer for this one would be, if we equate that to 0, would be x equals minus 1 over 6. Equate that to 0, x equals 1. So one of the applications of factorization is solving equations. So we come to surds. Surds are non-ending and not recurring decimals. So example could be square root of 2. So it is not ending and it is not recurring. It is similar to a pi, for example. Or we can say that they are not rational numbers. So two main rules in here. First of all is that square root of a times square root of b equals square root of ab. And the second one is that square root of a divided by square root of b equals square root of a over b. So these two are the main rules that we need to look when we are dealing with surds. There are some other rules that we can have a look, but they come from one of these. For example, square root of a times square root of a. Based on this rule in the first rule that we had in here, this would be square root of a times a, which is square root of a squared. So what is square root of a squared? This is square root of a squared. So the answer would be just a. It is like saying, what is the square root of 4? Square root of 4 is 2, but why is that? Because 4 is 2 to the power of 2, and that is square root, so this would be just 2. So square root of anything times itself would be just a number coming out of the square. Okay, so we will look at some other applications, but these two in here are the main rules that we will be applying into for surds. So for surds, I'm just going to basically solve an example, and I want to combine that example with also indices and simplification of, if you like, comparison of interconnectivity between power fractions and surds. If you remember, we had this rule in surds, which was a to the power of n over m equals root m of a to the power of n. So I'm just going to start with one example in here, and that would be the case of 9 to the power of minus half. So if I want to simplify that, first of all, based on the minus rule that I had in indices, I can take the minus off, but put everything into make a reciprocal. So this would be 1 over 9 to the power of plus half. 1 over 9 to the power of plus half. And now I can use this formula here, and that would be 1 over square root of 9, or 9 to the power of 1, which is 9. Square root of 9 is 3, which is, that answer would be 1 over 3. Okay, so I'm just going to do one more example, which is could be slightly more demanding. So this time I'm going to do 27 over 8 to the power of 2 over 3. So we could use surds in here to solve, but again, if you look back into the indices rule, we can first of all separate this in here. We can say this is equal to 27 to the power of 2 over 3 divided by 8 to the power of 2 over 3. And then we can basically say that this would be root 3 of 27 to the power of 2 divided by root 3 of 8 to the power of 2. The rules that we had, if I just reverse use this one in here, 27 to the power of 2 is 27 times 27. So I can basically write this would be square root of 27 times, root 3 of 27 times root 3 of 27. divided by root 3 of 8 times root 3 of 8, because we have 8 to the power of 2, so I can write it twice and then separate that from this rule. So root 3 of 27 is 3, root 3 of 8 is 2. So the answer would be 3 times 3 divided by 2 times 2, which would be 9 over 4. So this was when we wanted to apply surds, but I can use, we can also try to avoid doing this with just using fractions, and we could avoid using surds to solve that. So I am going to start in here and say, start from beginning, 27 over 8 to the power of 2 over 3. So I can say in here is, I can separate, again, if you remember, we had a to the power of n to the power of m equals a to the power of nm. So we could also go from this side to that side. So I can separate that 2 over 3 to 2 times 1 over 3, because that would, I know that 2 times 1 over 3 would be 2 over 3. So we need to use this, we need to solve some examples to get used to this simplifications or manipulations. So we have in here 27 over 8 to power of 1 over 3, all of that to power of 2. We write this in here because 2 times 1 over 3 is equal to 2 over 3. So 27 over 8 to power of 1 over 3 basically means square root 3 of 27 divided by 8. So root 3 of 27 is 3, root 3 of 8 is 2. So this would be 3 over 2 to power of 2, and that would be 9 over 4. So you will still get to the same answer with slightly shorter approach. Okay, it is important that, as I said before, to be able to manipulate different algebraic expressions using indices, and we need to be able to use all of the indices rule in different forms. And I'm not going to focus in that area because that is a GCSE part, and you will find videos on the site that it would focus on using indices. So the other example when we apply the surd rules is when we are manipulating surds, and when I say manipulating surds, and in a different form, when we want to simplify surds, or and I just give you an example here. So I'm just going to give an example from a book that I have in here. So because this would be a larger example, I'm going to go to the next page. Again, it's an important example to see how we can use different formats, rules for surds and simplify cases. So the equation is simplify square root of 12 plus 3 square root of 48 and plus square root of 75. So we want to simplify this. It could be difficult because look difficult because we can't use any of the rules that we had in previous page. Because if you look at here, we have time or divide in these two rules. But the page that we see on the other side, the simplification, is just plus, and we don't have any time or divide. The trick in this sort of examples is that we need to simplify all of these surds as much as possible. So, which is a point that I want to go through it in this example. So to simplify surds, I'm going to look at 12 and write the prime factors. So divided by 2 is 6, divided by 2 is 3. So basically 12 equals 2 to the power of 2 times 3. So when I say square root of 12, I can say that is equals square root of 2 to the power of 2 times 3. I can separate that from the rules that we had. That will be square root of 2 to the power of 2 times the square root of 3. Square root of 2 to the power of 2 is 2. So that would be 2 times square root of 3. I just can write 2 square root of 3. So 2 square root of 3 in here means 2 times the square root of 3. So that is how we basically show these surds with numbers. So I'm going to, instead of that square root of 12, I'm going to write 2 square root of 3. Now, in the same way, I want to simplify square root of 48. So again, if I look at the prime factors, that would be 2 is 24, 2 is 12, 2 is 6, 2 is 3. So 48 is 2 to the power of 4 times 3. So square root of 48 would be square root of 2 to the power of 4 times the square root of 3. The reason that I separated like this, because I am looking for an even number in here that can simplify with the square root and give me a full number. So I separate that 48 to 2 to the power of 4 times square root of 3. So 2 to the power of 4, which is 16, square root of 16 is 4. So 4 times the square root of 3, this would be 4 square root of 3. So this would be 4 square root of 3. So this is in here is 4 square root of 3, but we also have a 3 times that. So 3 times that would be plus 12 square root of 3. Finally, I need to simplify the 75. I'm going to write it down just as one go rather than going through details. 75 equals 3 times 25. So square root of 75 would be square root of 25 times the square root of 3. Square root of 5 is 5, so this would be 5 square root of 3. So I'm just going to add that in here, 5 square root of 3. After doing all of this, as you can see, we now have all of these terms that have the same term, which is square root of 3. So we can simplify this, 2 square root of 3 plus 12 plus 5. That would give us 19 square root of 3 for simplified form. Okay, so it is very important for us to be able to simplify surds, and we will use it in different subjects, including sometimes solving quadratic equation and simplifying that final answer. My final page today is about rationalization of fractions with surds, and mainly we have two different forms, and we do rationalization to simplify the fractions. Fractions and surds basically. So we do rationalization to simplify fractions that they have surds. Now, to give you an example, for example, we look at 1 over square root of 2. Rationalization means we want to remove the surds from the fraction of from denominator of a fraction. So as you can see in here, denominator of 1 over square root of 2 has a surd. So we need to remove that, and that form will we call it rationalized form. So to remove that square root of 2, what we do, same as the basics that we know about fractions, again from GCSE, 2 over 4 equals 4 over 8. We can time both sides to the same value, and that will still be the same fraction. So I can basically equate that and time the numerator and the denominator to square root of 2. So this would be 1 times the square root of 2. This would be square root of 2 times the square root of 2. And we know that square root of 2 times square root of 2, as I just mentioned before, that would be just 2. So 1 times that would be square root of 2. So 1 over square root of 2 becomes square root of 2 divided by 2. This is a rationalized form because we don't have any surds in denominator. So sometimes rationalization does relate results in simplification of the fraction. So the example is square root of 7 over square root of 63. So again, this time I am going to time both sides again to the denominator. So this would be equal to square root of 7 times the square root of 63 divided by square root of 63 times square root of 63. So we time both sides to square root of 63. So this would be, now the denominator would be just 63. The numerator, this would be square root of 7 times square root of 63 is 9 times 7. So that would be square root of 9 times the square root of 7. Again, this is the rule that we apply. So this is square root of 63 together. But square root of 7 times square root of 7 at the top becomes just 7. The square root of 9 divided by 63. Now 7 and 63 can simplify. So divided by 7, this would be 9. So square root of 9 divided by 9. So this is a rationalized form. So as you can see, when we have just one surd in denominator, the way that we do rationalization, we just time the numerator and denominator to that surd denominator both sides. And the reason that we do that, because we know that this times itself becomes a number. Square root of 2 times itself becomes a number. So I call this form number 1. So what so far we have done is form 1. When we look at form 2, form 2 are the examples that the denominator is not just one term. For example, we can say 1 over 3 minus the square root of 7. So 1 over 3 minus the square root of 7, as you can see, the denominator is not just one term. It is 3 and also minus the square root of 7. So we have two different terms. This time, if we time the denominator and numerator both into 3 to the denominator itself again, it would not work. Just to show that it would not work, I'm going to do it. So 1 times, I'm going to time again 3 minus the square root of 7. This would be again 3 minus the square root of 7 times 3 minus the square root of 7. So the numerator would be just 3 minus the square root of 7. The denominator, I need to time and expand all of these. So 3 times 3 is 9. 3 times minus 7 is minus square root of 7 is minus 3 square root of 7. Again, minus the square root of 7 times 3 is minus 3 square root of 7. And minus square root of 7 times minus the square root of 7 plus 7. So the answer would be 3 minus the square root of 7 divided by 16 minus 6 square root of 7. Have we exceeded in rationalizing this? The answer is we have not, because we still have surds in the denominator. So we really did nothing on rationalization because we had the surd in denominator here. By timing this to itself, we could not remove the surds. So in the form 2, timing to denominator itself is not the answer. So what is the answer? I am going to do the same question, same example in different form. So I'm just going to look at in here 1 over 3 minus the square root of 7. So the answer for form 2 of rationalization is we need to time this to a term that would make a difference of 2 squares. So if you remember, we had a squared minus b squared equals a plus b times a minus b. So we need to, if we have a plus b, we need to time it to a minus b. If we have a minus b, we need to time it to a plus b. So if we have 3 minus the square root of 7, we need to time it to 3 plus the square root of 7. So that is what we are going to do. So 3 minus the square root of 7, which is that, times 3 plus the square root of 7. So if we time this to 3 plus the square root of 7, we need to do the same thing to the top, because we need to keep that fraction still same, left and right same. So we are timing both sides, numerator, denominator, to 3 plus the square root of 7. The reason that we time it to make a difference of the square is that now from here we can say that this is equal to a squared minus b squared. So what that basically means, this in here, this is my a and that is my b. So a squared would be 3 squared, which would be 9, minus that minus in here, so that's, I'm just writing the same thing, minus b squared. B is a square root of 7. Square root of 7 squared would be just 7. At the top I have 3 plus the square root of 7. I simplify a bit further, 3 plus the square root of 7. 9 minus 7 is 2. So as you can see, now I have succeeded in rationalizing because my denominator is just a number. So form 2 can have very different forms. I'm just going to put 2 more, the same form but in a different shape, but it is the same thing. You could have 1 over square root of 2 minus 1. So to rationalize this, 1 times, again, we want to make a difference of 2 squares. So it will be square root of 2 plus minus 1 times the square root of 2 plus 1. And you will continue. The other form would be something like 1 over, or I can just basically, it doesn't need to be 1. I can just put square root of 2 plus square root of 5 over square root of 2 minus the square root of 5. So with this form, see, the fact that we have now a numerator changing, numerator changed should not make any difference. The only difference that it makes is that we will need to just do a bit more operation at the top, but the overall thing, it has no effect on what we need to do. With this one, again, we need to do a complete square, difference of 2 square. So that would be square root of 2 minus the square root of 5 times the square root of 2 plus the square root of 5. Because we are timing the denominator to square root of 2 plus square root of 5, we need to do the same to the numerator. So square root of 2 plus the square root of 5, square root of 2 plus the square root of 5. So we time both sides to the same thing. That is the way to make sure that the fraction is the same. Now, again, this would be difference of 2 square. Square root of 2 squared would be 2. Minus square root of 5 squared would be 5. At the top, we just need to time them together. So if we time them together, if I simplify it and write it in here, you try it at home and you will see this would be the simplified version. So that would be 7 plus, so 7 plus 2 square root of 10. So that would be, if you time that and simplify. So the final answer would be 7 plus 2 square root of 10 divided by minus 3. We can take the minus out, it's the same thing, so it would be minus 7 plus 2 square root of 10 divided by 3. So this covers the first chapter of core 1, and this is still a review from the GCSE Maths, just mainly on algebra, which should prepare you for next chapters and starting new look at algebra in core 1 compared to your GCSE studies. So for more videos, you could follow our YouTube channel for updates for future videos.